that's nice. Oh. So. Okay, so we also talked about this hypervalency. Okay, yeah, I remember. So we did do this slide. Okay, now and then we started talking about this, the hypervalency. We were talking about the ion pairing, but we didn't get to spend a lot of time on that. So let's just double check to make sure we understand. Okay, so hypervalency, of course, you remember that's where the heavier atoms start breaking the octet rule. So for example, if we have chlorine trifluoride. So what you're looking at for chlorine has 2 lone pairs on it. So now you notice that chlorine has 10 electrons around it. But what actually starts to happen in molecules is, so at some point, a fluorine comes close to a chlorine. So it doesn't really matter where you steal it from, but this fluorine is going to take an electron, which is then going to leave a negative, a positive. So like that. And so then you see these 2 open areas on the chlorine. Those are just going to straight bond 2 fluorines. So we have our positive charge. And then what happens is the fluorine, the negative fluorine comes in, or the fluoride ion. And this third bond is not really what we would know as it's not a covalent bond, it's an ionic interaction. So this is how molecules are still obeying the octet rule. They're playing with these ion pairs. So let's take a look at these 2. We have a molecule and an ion, and let's see if they follow the octet rule. Well, arsenic F5, arsenic pentafluoride. So technically, the first way you could draw it this is the way we would have done it in Gen Chem. And so we see the hypervalent arsenic, but let's think about, again, kind of like what happened above. Fluorine's going to come, and so your arsenic starts with 5 valence. A fluorine comes, and it's going to steal an electron. That's going to give us a positive arsenic. And a negative fluoride. And so then we have those 4 spots on the positive arsenic. So I don't know, just for fun, let me to kind of leave a place open. I'll put fluorides here. And then you have that positive region open. For the negative fluoride to come in and electrostatically bond at that location. And so now we end up with our arsenic ASF5. And so this is non-metal, so technically it still falls into the covalent realm. So we would still name it arsenic pentafluoride, even though it's not a fully covalent molecule. What about the aluminum H4 negative?
How many valence electrons does aluminum have?
Yes. Aluminum has 3 valence,
Ooh.
but it needs to bond 4 hydrogens. So that means an electron is going to come in. We're going to get that negative charge. So then all that happens is the hydrogens come in. And they bond, but the hydrogens don't get rid of that negative charge, so it still retains that overall negative charge because the aluminum had to pull in that extra electron. So this is kind of this is a look at isoelectronic structures, which goes much deeper than what we did in Gen Chem. You see that a lot of structures are going to be isoelectronic with each other. And despite what we may think, the octet rule is still pretty much strictly obeyed.
Pretty much.
Well, you'll see structures like this.
Sure.
But we know that we're really going to get that ion pairing, and then we're going to start, and then we will also get resonance within the molecule. So all of those fluorines will end up kind of passing around the ionic charge. And so then you're going to kind of, so essentially what you would get where none of them are technically strictly covalently bonded, but they kind of are, because they're just going to be passing all that around in resonance. That's because wave functions can just shift around each other. Yeah, it's kind of fun once you get to the point where you realize inside molecules, things are much more fluid than you thought they were.
Yeah.
Yeah, in Gen Chem, you get this real like rock solid, like this is the way it is. It's like, no, actually, when you're dealing with electrons, it's much more fluid than that. You always got to start thinking of electrons in one of 2 ways: either a cloud that wraps around the molecule and can shift, or as waves in a fluid that are just going but can be altered based off the needs of the fluid. So, electronegativity. So we learned about this as a trend, but we've never seen any electronegativity actually calculated. So we're going to look at 2 in particular. And again, they're using the Greek letter chi to represent this. So these are the Pauling electronegativities. So of course here the enthalpy of actually dissociating a molecule is going to be 1/2 the, let's see, what did we say A was? Please tell me I wrote it down. Yeah, I need to review the book again. Basically, it's the enthalpy of these 2 atoms associating with each other. And it's going to be 1/2 that D is your dissociation energy. And so your XX is, imagine like a diatomic molecule. And so that's representing like the molecule at the bond in the middle. And so it is really going to end up pretty much being like 1/2 the bond energy.
Sure. So that doesn't represent X minus X. It's
No. It's just imagine like O2. It's like oxygen. So really, we're looking at the energy of pulling those 2 atoms apart. And so the enthalpy of this system, I just forget what the subscript A means because I didn't write it down. But the enthalpy of this system is going to be 1/2 that dissociation energy. Okay. So basically, the way electronegativity was discovered was, again, there was theory that talked about, let's see. There was theory that talked about separating molecules and what they called a homolytic cleavage. What do you think homolytic cleavage means?
That's when like each atom when they split takes one electron.
Mhm. They each take away one electron out of that bond. But then experiments started to show that this wasn't exactly true. That there were some atoms that split heterolytically. So electrons were either going this way or that way. Every now and then they'd split homolytically. Like most of the time your H2 will split homolytically. But you start like hydrogen fluoride does not.
Right, the fluorine takes.
Yeah.
All of
And so they started getting these different values and experiment going, well, something's happening here. And they came across this idea of electronegativity, saying some of these atoms pull electrons towards themselves much harder than other atoms. Again, you can also relate a lot of this back to the effective nuclear charge of a given atom. So it's like for fluorine, you'd see one of the highest effective nuclear charges on the periodic table. So here we go. And so then we can also estimate the dissociation enthalpy of a heteronuclear diatomic. So up here is your homonuclear diatomic. So X and X are the same atom. Here, let's say it's like carbon monoxide. So again, it's going to be 1/2 of the dissociation enthalpy of, let's say if it's carbon monoxide, your XX would be oxygen, your D would be a carbon-carbon bond. Okay? So here, estimate the bond dissociation enthalpy of hydrogen bromide. If the D of HH of hydrogen is 436 kilojoules per mole, and the dissociation enthalpy of bromine is 193 kilojoules per mole. Compare this answer to the experimental bond dissociation enthalpy of 366 kilojoules per mole.
Okay.
So the way, instead of XY, what we would use, D, H, PR, 1/2, D, HH, plus D. What? Not going. Still, okay, it's still going. Okay, whatever. So this is how we would set that up, and putting our atoms in for X and Y. So we're going to get 1/2 436 plus 193. And we actually get about 314.5 kilojoules per mole. Well, that's quite a bit lower than the 366 kilojoules per mole. So this is what they were discovering experimentally. Why? Can you explain to me why the actual dissociation enthalpy is higher?
I mean, is it just because is it because of that homolytic bond cleavage? Like one of them just has to take both of them?
Yeah, so which atom, so it's going to be a heterolytic cleavage.
Sure.
And which one do you think is going to take the electrons?
Probably the bromine.
The bromine. Now, the reason the enthalpy goes up so much is not only is it taking the electrons, but can you explain to me what it's actually like when it takes that electron? What's it really doing? Where is it taking the electron from? What does it have to do to get that electron?
I mean, it's ganking it out of the hydrogen's S orbital, right?
So you have an electron in a stable orbital
Mhm.
on the hydrogen. The bromine has to strip the electron out of that orbital, essentially ionizing hydrogen, which of course, I still say that hydrogen ions don't exist. They only exist as H3O plus in solution. Otherwise, they're nucleonic radiation because it's a proton. But still, you have the one electron in that stable 1s orbital. And the bromine has to completely separate the electron from the hydrogen. So that's going to take that's going to take more energy to do that. So Linus Pauling was one of the first ones to look at electronegativity. This one here is not the most accurate, but it can still be used for quick estimates. It's also pretty historic to chemistry. We all know the name Linus Pauling. So if I could, I would use Linus Pauling's general chemistry textbook as our Gen Chem textbook, but that would mean you'd have to be doing calculus as a freshman.
Oh, no.
I mean, you could have done it.
I could have done it, but I feel like that class would be really, really small.
It would. So now we get to a better estimation, which are called Mulliken electronegativities. Now, these are important because first off, in computational chemistry, when we're making estimates, so every atom in a molecule is going to have a slight charge on it based off its electronegativity, its electron affinity, all these different things. Every atom is going to have a charge on it. We use Mulliken electronegativities to calculate what are called Mulliken charges, and it gives you an estimate of the charge distribution on each atom of a molecule. So when we start to calculate, you can go into the output folder of your calculations and find your Mulliken charges and start to get an idea of charge distribution throughout the molecule. And then, of course, you can take that into the lab, do some experiments, and with that estimate of charge distribution, you can start to get a more full picture of what's happening in reaction. Like, why was this energy so much higher or this one so much lower? Okay, well, look at that atom there. You see all the charge on it? Well, that's why. It's like one of the worst chemotherapy compounds we have is called 5-FU, and it's basically a fluorinated imidazole. And because of that fluorine on there, that fluorine takes up a lot of partial charge to itself. And what it does is it ends up short-circuiting cellular membranes so that they start allowing everything through.
See.
So, as you're doing research with, molecule experiment, you can't actually see the molecules. Sometimes it's kind of nice to have a quick calculation to have an idea where all this goes. So Mulliken became very, very important. And so what you see there is, of course, let's see. So basically what Mulliken says is, imagine you have a diatomic. And so as you're splitting that, for each atom in there, you're going to be looking at about the electronegativity of an atom will be 1/2 the first ionization energy of that atom plus the first electron affinity of that atom. And so it's going to be an average between the energy needed to strip an electron and the energy of the atom to pull to want an electron. So we know electronegativities are usually going to be exothermic because as an atom with a high electron affinity takes an atom to itself, it stabilizes and releases energy. So, okay, dipole moments. Now, this is the equation for a bond dipole. So when you look at the overall dipole of an entire molecule, that's a vector sum of all of the bond dipoles. So you want to really kind of map the bond dipoles, split them into their components, look for the vector sum. That'll give you your overall dipole moment of a molecule. Here we're looking at the dipole moment of individual bonds. And so mu is going to be your dipole moment. And it's going to be charge times the base. So let's see, the charge on the atom times the base charge times the distance between the two atoms. Okay. We can use this as another way to start calculating charge distribution in atoms. Okay, well, let's say for hydrogen fluoride, we have a bond length of 92 picometers and a dipole moment of 1.83. What's the D? Have you ever seen that D before?
Is that Dalton's?
Debye.
Debye? Okay.
So it's a new type of electric representation.
Okay.
So the question becomes, what is the charge going to be on each atom? What is the approximate charge going to be? Okay. So let's just go ahead and write down our hydrogen fluoride. So then we're going to take our bond dipole and we're going to solve it for the charge of a given atom. Okay. Now, we can't really use dipole in this calculation because E is in coulombs. So let's see, a nice little thing for you here. 1 dipole equals 3.336 10 to the negative 30th coulomb meters. And so this will be your nice little, so you can see it's charge, a dipole is charge across the distance.
Right.
And so then what we're going to have is our Q will be, so our mu is, oh, let's turn it into, let's try to change our dipole. It's 1.83 dipole. And we're going to have 3.336 meters by, that is going to give us 6.105 10 to the negative 30th meters. Now we can solve. Q, let's see, the base charge is 1.602 10 to the negative 19th coulombs. Then we have 92 picometers. What is times 10 to the what?
Negative 12.
Mm-hmm. Negative 12 meters. Then we're going to have 105 10 to the negative 30th coulombs times meters. So our Q ends up being 0.41. Now this is weird because you want to have a unit on Q, but when we're dealing with dipole moments, these Q's are going to be unitless. But in this case, what do you think this is telling us? Look at the hydrogen fluoride up there. This charge distribution is going to be about 0.41.
0.41. Does that just indicate that it's like unevenly shared?
It is. And the way you look at this is across this bond, your dipole is going to be represented as a positive 0.41, and then you have a negative 0.41, and that is the charge distribution across this bond. So as you go through, you'll see stuff like this more and more often. Well, this is where it comes from. These are numerical representations of the charge distribution across a bond dipole.
And you do that for every bond.
Mm-hmm.
Yep.
Right. And so, of course, it becomes much more complex when you're in a bigger molecule, like say an organic molecule, because then across each bond, you say, well, you have a carbon here, carbon, 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 hydrogen. You're going to have to do this for all the bonds, and then it's like, well, how much does each carbon actually hold? It ends up becoming a process you really want to write a computer program for. So, okay. Molecular orbital theory for heteronuclear diatomics gets a little more complex. Okay, so let's just start here with hydrogen fluoride. Okay. So let's get an idea of what we're looking at here. So you remember how we talked about orbitals needing to be pretty well symmetric to form molecular orbitals? The problem we start to get with heteronuclears is you notice that your Z effective is going to be different for each atom. So not only is this going to facilitate mixing, and you'll see that in more detail when I go down a slide, but you're going to see, for example, here, like in carbon monoxide, the oxygen orbitals lie lower in energy than the carbon orbitals. So they're still going to be symmetric, but the overlap will decrease a little bit based off the different energy levels. So this becomes quite a bit more complex. So here, for example, also take, for example, your hydrogen fluoride. Your hydrogen only has the 1s electron. Your fluorine is going to have, but it has helium as its core, and then it has 2s2, 2p5. So it has all of those extra electrons. So we're not even worried about the 2s level right now. So that 2p5, You notice how the 1s is up in energy with the 2p. This is what we mean by you're getting some significant mixing here. That 1s doesn't go down in energy to the fluorine 2s level. Those fluorine 2s electrons are going to be non-bonding. They're just kind of sitting there. Whereas this 1s electron comes up, and yeah, it forms that sigma bond that we know with one of the 2p orbitals, but then you still have you have two lone pairs just sitting there. And those lone pairs aren't going to bond. They're not going to contribute to bonding or anti-bonding. They sit somewhere in the middle, and those are called non-bonding. So they're still there, but you notice here you have the bonding down at the bottom. You have your two-dimensional non-bonding orbitals. So that would be, your symmetry would be a two-dimensional symmetry, like we talked about.
Right, the linear.
Yep, because those are going to be degenerate, and you have multiple of them. If you had three of those, you'd get the symbol T for a three-dimensional degeneracy, and so on and so forth. As we go through, you're going to get sick of capital E because it starts to mean different things.
Yay.
It stands for a two-dimensional degeneracy in symmetry. It's also a symmetry action, called the identity. But we'll deal with that in the next chapter.
Yeah.
And so then, of course, up at the top, you see the antibonding orbitals. Well, let's look at this in greater detail. Okay, so for the fluorine, you see the 1s and the 2s level. You see that hydrogen 1s orbital goes way up in energy due to the fact that even though that electron sees the entire proton, you still only have the one proton. Fluorine has a good deal more positive energy pulling on its electrons. So it's pulling those p orbitals and s orbitals closer into the nucleus and lower in energy. Let's see. So then, of course, we get the 1s, which is going to sigma bond with one of the two p orbitals. And again, that's where we're getting that sp mixing. But one thing to keep in mind, another thing that starts to destabilize molecules is if I went out here, so I have that orbital there, and then I'm just going across here because that's the energy level that our 2p orbitals are at. The delta E we're talking about is right there. The larger that delta E becomes, the less and less overlap you get. So the bonding gets weaker and weaker and weaker as those orbitals become further apart in energy. So again, you can see that the best bonds really come with orbitals that are identical in energy, and they have the right symmetry. So like your homonuclear diatomics have very strong bonding. So again, like we said, once the bond forms, well, hydrogen's out of electrons. The 2p level is not, but they're already stable because they're in lone pair configurations. So they're just going to kind of hang out there in the middle of bonding, anti-bonding energy-wise, and those are going to be non-bonding levels. We can get a better look at this. So this was fun, making these. So I actually calculated these. And sometimes they're easy to see, sometimes they're hard to see. Let's see if we can figure out why these are called. And so forget the 1s, 2s level. Okay, at the 2p, here's your sigma. There's your non-bonding. There's your antibonding. Okay. So let's take a look at these and try to figure this out. Yeah, you see two different phases here.
Yes.
And can you see the sigma bond?
Yeah.
Why can you see that?
I mean, it's the one that got misshapen a little bit.
Well, are you talking about this one?
I think so.
So why would that be a sigma bond, even though we see two orbitals here of different phases that we know are not going to create a bond?
I mean, it's the mixing thing, right? Like they kind of
It is. But when you're looking at orbitals, say at articles or whatnot, you see how this extends all the way across the bond from the hydrogen over to the fluorine? It actually envelops the bond itself. So we're not even worried about this orbital. This one right here is your sigma orbital. because you had the proper symmetries and the hydrogen 1s mixed with a 2p, and you got this bond. And that's why this s orbital got elongated a little bit. And so it reaches all the way across the bond, and it reaches to the fluorine. So that is going to be your bonding orbital. And again, we just don't even worry, whoopsies, about that one. So here we have our non-bonding levels, because you can see if you look at this one, these are p orbitals solely situated on fluorine. They reach over into hydrogen space, but they have nothing to do with the hydrogen. That is where your lone pairs are sitting. And of course, you have your doubly degenerate non-bonding level. This one up here is a little fun.
Yeah.
You can see what appeared to be an s orbital on the hydrogen starting to do something, but if you look here, here's your fluorine, so it's kind of going back into the board at an angle.
Yeah.
I tried to get this so you could, as the best you can see it. You notice on the fluorine how you have this phase, the two phases on the fluorine. Now this phase is on the outside of the fluorine, so it's not doing anything. As you look in here, you see the other phase, which is the phase facing the hydrogen. So then you can imagine, that's why you got this explosion of the orbital and you got this dent in there, is because this green phase in there is actually pushing away electrons, because those are going to be anti-bonding in their interaction. They're completely out of phase with each other and the symmetry is all wrong. So right in there, you have this phase interacting with the opposite phase across where the bond would be, and that's causing an anti-bonding interaction. Sometimes it takes a while to learn how to read these if you're ever looking in articles.
Yeah.
Okay, well, let's go a little more complex. Let's look at carbon monoxide. Here you can really see the SP, the SP mixing. Because again, we talked about this, the oxygen, greater effective nuclear charge, and it starts pulling its orbitals down lower in energy. You can see that with the 2s and 2p. Now look at the structure there. You have the carbon 2s and 2p that go up in energy, but look at that 2s orbital and how it's forming sigma bonds with both the 2s and 2p levels of oxygen.
Yeah.
That's what we mean by mixing.
Mm.
It starts giving character to so 2s character to both the 2p and 2s level.
Mm.
So if we start thinking about this way down there at the bottom, and this is something else you'll see, that they're labeled 1 sigma, 2 sigma, 3 sigma, 4 sigma, and they line up with the sigma, sigma star, sigma, sigma star. But you'll see them labeled this way just to denote that these are different sigma orbitals at different energy levels. And it's some jargon to get used to. Then you have your pi and your pi star. So let's see, what did I say here? So if we start looking here, you also notice, so let's see, that's 1, 2, 3. So your 3 sigma here is your bonding between the 2s and the 2p, okay? So you notice though, once you get over here on the side of the carbon, that much larger orbital. So again, you can see the bond right here in the middle. So that's going to be your sigma bond. But since you're getting the mixing of, so you see here how you're getting 2s and 2p character from carbon in that sigma bond. That's why this orbital is larger. You get more carbon character in the orbital than you do oxygen character.
Right. So okay, like this is like an example of it being like a cloud or kind of like a fluid,
Mhm.
like it's
Mhm.
going wherever it needs to be.
Mhm.
I see.
And see, and as you start to see these characters that dominate, again, you have 2s and 2p both mixing together with the oxygen 2p to make a sigma bond. That larger carbon character is going to greatly affect the reactivity of the molecule.
Mm.
So it's going to behave more like carbon would than it would oxygen. Oxygen's just going to kind of be off, and which makes sense. If you looked at your organic molecules, you see your rings and you just see the doubly bonded O just kind of sticking out in space. Well, that's because of stuff like this. This carbon monoxide could join with other molecules to start forming those organic compounds, because of the dominant carbon character. So again, we could go through and we could do symmetries on all of these, but you've kind of got the idea of how that works. Let's see. So again, we have a funny little divot in there, but that's clearly a sigma bond which reaches all the way across. These two, this one looks kind of similar, but what's hard to see is right there in there, there's a divot. And because of that divot, we now have a sigma star character. And here's your doubly degenerate pi bonding, so the pi 2p level, which your pi bonding, of course, as remember we talked about, only is going to come from p orbitals. So sigma is not going to perform a pi bond. And that's real basic. You can think of sigma or S as a sphere. And so it can't have an up and a down. No matter where you hit it, you're head on. So it's always going to be a sigma bond. So again, your pi bonding can only come from p levels.
Right, because it's the parallel.
Why can't pi bonding come from d orbitals?
From d orbitals?
Well, let's see. Is that correct? I may be talking too fast here. Let's think. Well, what's the predominant bond d orbitals will make? So p is the Greek letter for, or pi is the Greek letter for p. D orbitals will make what kind of bonds?
I mean,
delta bonds.
Delta bonds?
Yeah.
Is that true? What is a delta bond?
So you remember the pi bond where you have a p orbital up and down, and they reach across?
Yeah.
Now imagine you have d orbitals, like the four lobes, and they all reach across and form another bond.
Oh.
So, and then of course up here we get to this sigma level, our doubly degenerate pi star level. So we see those two. This one was kind of fun. That's your antibonding sigma, which of course you can see it just goes phase to phase to phase to phase across the entire molecule. And so you're getting all that antibonding repulsion. But getting used to molecular orbital structures like this is going to be important. So you want to be able to read the mixing. You want to understand the stronger carbon character in this sigma bond than the oxygen character, because of course, yeah, you're going to get pi bonding and whatnot, but that character, of course, is going to really affect reactivity. And having an understanding of all this stuff is going to help you with articles. It's going to make things start to make a lot more sense in the laboratory.
Sure. Yeah.
So this was a more advanced look at molecular orbital structure. Now, but like I said, as you get to more and more complex molecules, we're still doing sigma stars, pi, stuff like that. Eventually, you get to a point where your entire energy structure is just based off orbital symmetry, because the molecule is just too complex to do this way.
So when they're looking at this and they're finding out which order to put it in, because you're talking about how kind of what is it, that other sigma orbital or the sigma bond will kind of go above and below the pi.
So here,
did they figure that out experimentally? How do you know when those switch, which one has more energy?
Well, so yeah, I mean, a lot of experiment has been done. Again, we kind of go back to spectroscopy, and there's various other tests that you can use light for. You can, I don't know if they use it for this, but you can learn a lot from UV vis testing. So ultraviolet visible light testing. So there's just a lot of experimentation, getting results that you didn't quite expect, like with Pauling coming across the idea of electronegativity.
Right.
You expect a certain result, you don't get that result. You start to get molecules like, why is this behaving more like a carbon than it does an oxygen? Shouldn't it behave equally like both? No, but it doesn't, because you get and over decades, you start to build this image of, well, something is happening here. I know that the effective nuclear charge of one is much greater than the other, which means it must be holding its own atomic orbitals much tighter. And so we're getting a dominance of the carbon orbitals. They're higher in energy. They're closer to that chemically active range, like your homo-lumo gap. So they're going to be much higher in energy and much more available for chemical reaction. And so we actually start you start calculating energy levels of the various shells. you see, well, this, if you calculated the energy of this 2s by doing by looking at the wave mechanics, you see it's going to be very close in energy to that 2p. So since they're so close in energy and a sigma bond can form, there has to be some kind of character there where they're interacting with each other.
Right.
And we also know that we get sigma bond character from that 2p and this 2p. So you're having to get a mixture of both the 2s, 2p from the carbon sigma bonding with the 2p of the oxygen. So it's not something that happens overnight. It's a lot of experiment, a lot of theory, and going back and forth and saying, something is happening that we didn't expect. Is there a way we can explain this that will then predict what we're actually seeing? And this is where you get to. So yeah, a lot of this stuff is done in the high energy laboratories. And again, stuff like this is why spectroscopy is so difficult.
Sure.
It's really, really rewarding if you can get it, because you can unlock a lot of stuff going on inside of molecules.
Yeah.
But it is challenging. So, but that finishes up these first two chapters.
Yay.
And we're going to be moving away from quantum mechanics and orbitals. So you're going to see, as I said, next you're going to see symmetry. So we're going to start looking at symmetry operations, how you think about them all. But like I told you, the capital E, the identity operation has to be in every single character table, but identity is the easiest symmetry because you take the molecule and you do nothing to it. So a methane is a methane.
Sure.
So if I take the methane, I don't rotate it or reflect it or anything like that, it's E.
Okay.
So and then from there, we'll just, I have a couple of websites that I'll give you on Wednesday that can help you study symmetry elements like reflection planes, inversion points, rotational axes.
All right.
And we'll just start working our way through symmetry.
Whew. Yay.
Yeah, you can figure this stuff out experimentally. Takes a lot of work, a lot of focus.
Oh my god. Why am I step?